My name is Adolfo Campos, and today we'll explain the experiment of damp oscillations. The objective of this experiment is to see how different fluids affect the oscillation of a spring mass system and how is their damping effect. Okay, so first of all, for the first part of the experiment, we will need to know the spring constant K of the spring that we're going to use for the spring mass system. Here is a graph of the position of the mass against time. Uh, in this case, we don't have any damping. What we're doing is first we add a mass and we wait until it reaches a new equilibrium position, and then we add another mass, and so for 4 times. This is in order to get the spring constant, as we can get various points of the gravitational force with different masses and their respective equilibrium positions. So here in this graph, you can see there are some horizontal points followed by a vertical line. The vertical lines represent the moment we add the new masses, and the horizontal lines represent when they get to their equilibrium positions. So we need to plot 4 data points, as well as 0, 0, of these horizontal values as the position against their gravitational force. So here's this graph. Here you can see the 5 data points. And the slope of this line actually gives us the value of K, which in this case is 21.86, etc., as well as their uncertainty. This is important for the rest of the experiment, as with this value we will calculate the theoretical angular velocity the damp oscillation should give us. Okay, so for the second part, we actually had 3 fluids in order to test for damping. First air, second water, and third oil. How the experiment was made was that we have a specific mass, and we submerged it in a base with the fluid, respectively air, water, and oil, and record its position against its time. We actually give it a little bit of movement before starting, so we can see how it starts from a very high amplitude, and it gets lower and lower until it gets to 0. With these formulas, we can actually know the damping effect. So the formula we're going to use is actually an exponential formula, which is the formula for damping oscillations. And the values we have in order to calculate them is actually each of the peaks and valleys of each graph. For example, on air, we get this point, and then we get the absolute value of this point, and then from this point, etc., etc. This way we have more data points in order to calculate the exponential function, which is more important for the other fluids, especially oil, as there are too few peaks and valleys, as it damps the effect really fast. So for example, here we only have 5 data points we can use. So we actually get the absolute value of these peaks and valleys. Then we get the natural logarithmic of those values, and we plot that against time. And in theory, it should give us a straight line with a slope equal to minus the damping constant over 2 times the mass of the object. The damping constant is actually what we're going to try to know in order to compare it to the theoretical values. So when we do these calculations, here's what we get for each of the fluids. As you can see, air, there are a lot of data points, but it does not follow a straight line. As you can see, it varies a lot. It's not a straight line at all. Therefore, air cannot be expressed as the formula for damping oscillations. But in the case of water and oil, it actually follows a very straight line. So therefore, we can say only from only seeing graphically these figures is that both water and oil can actually be represented fairly accurately to the oscillation, to the formula for the damping oscillations. So also what you can see is that in air the value is minus 0.48, for water is minus 1.3, and for oil is minus 2.7. As you can see, it's getting lower and lower. The lower it gets, the faster it damps the oscillation of the object. And as you can see, there are less data points exactly because of that, because there are less times we can actually see an oscillation. So from seeing those values, we actually know that that oil is better at damping this mass than water, and water is better than air. Also, this value here, which is uncertainty, right below them, the slope of each of these best lines, is actually, here we represent it with the letter x, minus the damping oscillation represented by b over 2 times the mass. With this, we can actually know what the damping oscillation is. So here we calculate the values. You can see here in the top left corner the value of the damping constant of air. There are no more values because, as you saw in the previous graph, air is not very well represented with these formulas, so there is no useful case to go further from the equations and get more values if they are not accurate. But for water and oil, we can actually compare them. Here are the respective damping oscillation. As you can see, oil it's higher, it's double the one of water, so it damps faster. Here, the omega with apostrophe is actually the experimental angular velocity we get from the formulas we saw at the beginning, these ones. How we calculate it is using the positions. We got the average period, which is from peak to peak. And using the formula that compares to angular velocity using 2 pi, we actually got the experimental angular velocity. But we also got the theoretical angular velocity, which was used using the formula of angular velocity equal to the square root of the spring constant divided by the mass. Here is where we use the spring constant we calculated in the beginning in order to compare theoretically. As you can see, they are not far, but they are not close. There are errors of 21 and 31% respectively. This means that although they fit the straight line that is expected from the formulas, they are not that close to the expected values they give. Probably because it's not a perfect system, it's not isolated from everything else. Things like temperature and air density actually change their values, so therefore it's not exactly perfect. But from what we saw of the graphs, it can roughly be estimated as that. Thank you.